So if you have any question, any doubt, or if you face any problem, please feel free to say that immediately to me. And if you feel that I am going very fast, please feel free to ask me to repeat or slow down. That's absolutely fine. Okay. So we are discussing about the equivalence between a star connected resistive network and a delta connected resistive network. Okay, so let us continue that discussion. Okay, so suppose that these two circuits are equivalent. So we are starting with the assumption that these two circuits are equivalent. Now, if so, let us find out what should be the relation between RA, RB, RC and RAB, BC and RCM. Okay. So, since these two circuits are assumed to be equivalent, therefore, the resistance between A and B, the nodes A and B of the star connected circuit should be same as the resistance between A and B of the delta connected circuit, right? So therefore, now we can write the resistance between A and B in the star circuit is RA plus RB. They are in series, and node C is not connected, it's floating. And in the delta connected circuit, how much is the resistance between A and B? So we have RAB in parallel with RBC and RCA, right? So this is equal to, right side is AB RBC plus RAB RCA divided by RAB plus RBC plus RCA, right? In the same way, if we say calculate the resistance between, say, node A and node C, okay? So now considering the resistance between A and C, what do we have? So in the star circuit, the resistance between A and C is RA plus RC, and in the delta circuit between A and C we have RCA in parallel with RAB plus RBC. So the right side will be RCA multiplied by RAB plus RBC whole divided by RAB plus RBC plus RCA. Okay. In a similar way, now considering, say, resistance between B and C from the star circuit, the resistance between B and C is RB plus RC, and in the delta circuit this will be RBC into RAB plus RCA divided by RBC plus RAB plus RCA. Okay. So now if I call this equation 3, this is equation number 2, and let this be equation number 1. From these three equations, okay, let me add 1 plus 2 plus 3, these three equations, what do we get? So we will get on the left side 2 times RA plus RB plus RC, and on the right side we will get 2 times RAB BC plus RBC CA plus RCA RAB whole divided by RA plus RB plus RC. These two and these two can be cancelled. Okay, now if let me call this equation
RAB plus RBC plus RC in the bottom part.
Oh yes, thank you, thanks a lot. Yeah, many thanks. Yeah, RAB plus RBC plus RC. Yeah, thanks a lot. Okay, so now if you say subtract equation 4 minus equation 1, what do we get? Okay, so 4 minus 1, so we will get RC on the left hand side, and the right side will be RCA RBC by the sum of the three resistances AB plus BC plus CA. In the same way, if you subtract equation 2 from equation 4, you will get the value of RA, and similarly you can also get the value of RB. Okay, so you will get these three equations. So here we have shown that if these two circuits are equivalent, then let me copy from here. Okay. So then these three equations should be true, starting from the assumption that the circuits are equivalent. Now the reverse is also true, that if these three equations are satisfied, then these two circuits will be equivalent. Okay, but the reverse proof we are not going to do now, because that will take a little more time. Okay, then next, so here we see how to get the value of RA, RB and RC from the values of RAB, RBC and RCA. Can we also do it in the reverse way? That means, can we find out the values of RAB, RBC and RCA from the values of RA, B and C? Yes, it is possible. How to do that? The rule is as follows. So it will be RA, RB plus RB, RC plus RC, RA, okay, sum of the three products divided by, so let us look at the original circuit. Here the here we have RAB here, and RC is in the opposite position of RAB. Okay, so the resistance in the opposite position of RAB is RC, so we will put here RC. So this is the formula for getting RAB from RA, RB and RC. In the same way, can you tell me what should be the formula for RBC from utilizing the symmetry of the circuit?
Denominator will be RA.
Let me see. So for
Denominator
RBC,
will be RA.
the denominator will be RA. Absolutely right. The opposite resistance, opposite side resistance, RA. Okay, and similarly, RCA will have RB in the denominator. Okay. Now, let me give it as a homework that prove these three equations, the left side equations from these three upper equations, okay, these three red colored equations from the upper side equations. That means red colored equations. It's not very difficult, you can do it. Okay, so any questions so far? Anyone? Okay, then yeah, so yesterday we solved this question, okay, and I kept it as a homework to solve these three equations. So did any of you solved it and find out, did you find out how much is VA, VB and VC? Anyone? Okay, so what I got is this. VA, according to my calculation, came out to be 5 volt, VB 0 volt, and VC 10 volt.
VC is 10, VD is 0.
VD is 0, yes, right, yeah. So I hope
Yes,
my calculations are correct.
Yes, sir, I got the same.
So this is the answer, yeah. Now, today, let us learn another theorem starting from this circuit. Okay, so this is a circuit. It has 1, 2, 3, 4 nodes. Okay, A, B, C, and D, and let us choose any 2 nodes that you like. For example, you may choose this node, node C, and maybe you can choose this node. Okay, so let me just call this P and Q. Basically, they are same as A and B. Now, I have a question. If I define this current as I and this voltage as V between P and Q, okay, find the values of I and V when, so we have multiple parts of this question, when say a 2.9 ohm resistance is connected between P and Q. Next part, find the values of V and I when a 5 volt voltage source is connected between P and Q. Then say next part, a 2 ampere current source is connected between P and Q, and part D, when P and Q are directly connected, sorted. P and Q are sorted. Okay, so we have 4 parts of this question. The circuit is same, but now we can connect, we have to connect different circuit elements like a 2.9 ohm resistance. Here we will connect and we will find out the value of V and I. After that, we will replace this resistance with a voltage source of value 5 volt, okay, and we will connect it here, and we will find out the voltage V and current I. This is 5 volt. Okay, similarly then we will connect a 2 ampere current source and find out V and I, and finally we will just short circuit P and Q. Okay, we will connect them directly and find out the voltage and current. So this question has 4 parts. The left part circuit is always the same, but what we are connecting between P and Q, that is changing for the 4 different parts of this question. Okay, so how can you solve this? How would you like to solve this question? Any suggestion?
So by the voltage which we get from the previous question, nodal analysis.
Okay, so I got two suggestions. One is you can solve this circuit using superposition method or maybe nodal analysis, mesh analysis for these 4 different conditions. But that will take longer time to solve these 4 questions. Another possibility is use of what is called Thevenin's theorem. What is that? Let us learn first. Okay, so Thevenin's theorem says if you have a complicated circuit, no matter how complicated you like, okay, so as complicated as you can make, it's up to you. Think of any complicated circuit, okay, and then consider only 2 nodes that is of particular interest. So say this node and maybe this node. Okay, you may put more circuit elements here and there. So think of any complicated circuit, but we will consider only 2 nodes. Say this is one, this is another, P, Q, and then let me put the entire circuit inside a box, and these 2 nodes P and Q, they are outside the box. Everything else is concealed, is closed in a box. Now Thevenin's theorem and this circuit is made up of resistance, voltage source and current source.
Should all the 3 must be present, sir?
No, not required. So you may have only voltage source and resistance, you may have only current source and resistance. So all three are not required. Okay. Now, yeah, Thevenin theorem says that the circuit inside the box is equivalent to a voltage source in series with a resistance. This is terminal Q, this is terminal Q, PQ, and this is inside the box. Okay, and so the Thevenin theorem says that this kind of a circuit is equivalent to one voltage source, just one voltage source in series with one resistance, such that let me call the value of this source as VTH and resistance as RTH. TH stands for Thevenin, okay, and such that the value of VTH is equal to the voltage between P and Q in the original circuit when nothing is connected outside. And the value of RTH will be the value of the resistance between P and Q of the original circuit, or you can say of the circuit in box when all the sources are replaced by their internal resistances. Okay. So this is the theorem. No matter how complicated circuit you have, which is made up of resistance, voltage sources and current sources, this is always equivalent to one simple circuit made up of one voltage source and one resistance, such that the value of the voltage source VTH is equal to the value of the voltage between P and Q in the original circuit when nothing is connected outside, and RTH is the resistance between P and Q when all the sources are replaced by their internal resistances. Okay, so according to this theorem, now come to the question that we had. Okay, so first, for this circuit, so this circuit will also be equivalent to one voltage source VTH in series with RTH, our resistance. Now, how much will be the value of VTH?
Five volt. 5 volt.
How do you know that? Because
VC is 10 and VA is 5.
yeah, so we solved it yesterday that when nothing is connected outside, for this circuit VA is equal to it was 5, right? 5 VB equal to 0 and Vc equal to 10 volt. So Vth will be Vc minus Va, that is 5 volt. Okay, this we have solved yesterday. Okay, so this will be 5 volt. And now how much is Rth? Anyone? Sorry. To get the value of Rth, what do we have to do? We have to
21 by 10, sir.
right.
2.1.
2.1.
2 point.
That is
Yeah,
2.1. 21 by 10,
right,
2.1.
right, absolutely right. So what do you have to do? You replace this current source with infinite internal resistance. This current source is also replaced by infinite resistance. This source will be replaced by zero resistance, and this also by zero resistance. Sorted. So now let me clean it up a bit. Okay, now how much is the resistance between P and Q? We have two paths, 5 ohm plus 2 ohm in parallel with 2 plus 1 ohm. So this is equal to 5 plus 2 ohm in parallel with 1 plus 2 ohm, which is 3 into 7, 21 by 10 ohm. Okay, so that is 2.1, absolutely right. So this is 2.1 ohm. Now, if that is the case, if this original circuit is equivalent to the simpler circuit, then can you find out the answers to these questions? Okay, so what will be the answer when so here
1 ampere.
you are connecting
1 ampere and 2.9 volts, sir.
2.9.
right. So here we are connecting 2.9 ohm. So then this current is I and this voltage is V. Okay. So now how much will be the current? Here I will be 5 volt divided by 2.1 plus 2.9. So that will come out to be 1 ampere. And then the voltage V will be equal to 1 ampere multiplied by 2.9 volt, correct?
Yes, sir.
Then similarly, now if I remove this and put a 5 volt source,
Sir, is the direction specified? How is the source getting connected?
yes, I have given you the diagram here, right?
Okay, sir. Okay, sir.
Otherwise, we cannot solve it. Okay, so now this is 5 volt. So what will be the solution here? V will be
0 ampere.
0.
V will be 5
5
volt,
and I will 0.
but current I
5
will
volt
be
and 0.
5 minus 5 volt divided by 2.1 ohm, so that is 0, absolutely. And then part C, how much, so now we have a current source, 2 ampere, okay, so how much will be I?
2 ampere.
No, minus 2 ampere, okay, because you have to look at the direction, otherwise here is the I, okay, so I will be minus 2 ampere.
Okay, got it, sir.
Yeah, and then V will be
0.8 volts.
5 volt plus
0.8 volt.
2.1 into minus 2. Okay, so this is 0.8 volt, right? And then finally here, if P and Q are sorted, then I will be
I will be V by R 5 by 2.
by 2.1 ampere, and V will be
We will be 5
V will be 0 volt.
0.
Yeah, absolutely. Thank you. Okay.
Sir, at part set, part C, shouldn't it be minus in the V part? Like
In part C, we had a 2 ampere current.
V.
Yeah. Wait a second. Huh? So we had a 2 ampere current. Now, so 2 ampere is flowing in this direction. Okay. So how much is the volt? So if I call this A and this B, or let me call it this A and this B, then from A to B, the voltage drop is 2 ampere into 2.1. Oh, it should be added.
9.2.
It should be added. Right?
It should be 9.2, sir.
Yes,
Yeah,
sir.
it should be added. Thanks a lot. So into 5 volt plus 2 point into 2 volt, so that will be 9.2. Okay. Thank you.
Yes.
So any question up to this?
No, sir.
Then, so that's Thevenin's theorem. Next, there is also another theorem called Norton's theorem. Yesterday, we have studied that if we have a voltage source in series with a resistance, if this is say VTH, if this voltage is VTH and if this resistance is RTH plus minus, then this is equivalent to a current source in parallel with a resistance. This is what we have seen yesterday. Now what should be the value of this resistance in the current source? It should be
RTH.
RTH.
And what should be the value of
V by R.
VTH by RTH.
VTH by
VTH by
RTH?
RTH.
Okay, so now note that in the this left side circuit, if we let me call it P Q, if we sort P and Q, okay, if P and Q are sorted, okay, then how much will be this current? Let me call it ISC, SC for short circuit. Then ISC will be how much?
V by VTH by
VTH
RTH.
VTH by RTH.
Okay, so this is the this ISC is the value, is also the value of this ideal current source in the equivalent circuit. Okay, so this is also the value of the current source in the equivalent circuit. Okay, now with this observation, we can state another theorem, okay, which is as follows. Any circuit consisting voltage source, current source, and resistance when seen from any two particular terminals is equivalent to a current source in parallel with, let me call this current source value as IN, N for Norton, current source in parallel with a resistance, call that Rn. Okay, so if I come here, this circuit, when seen from outside, is equivalent to a current source in parallel with a resistance Rn In, where Rn will be the resistance between P and Q when all sources are
Replaced with their internal
yes, all
resistances.
sources are replaced by their internal resistance. And how much will be In? In will be the current, can you guess, that flows from P to Q when P and Q are shorted. Okay, so basically Rn is same as R Thevenin. So this is same as RTH, Thevenin resistance. Okay, and In is same as VTH, Thevenin voltage divided by RTH. Do you agree? Do you have any doubt or any question so far?
No, sir. Sir, and can you show the previous page?
Yes.
Sir, can you show the slide on which you wrote about Thevenin theorem?
This one? Okay.
Thank you, sir.
Yeah. So now,
Sir, is there any proof for Thevenin theorem? Like we short
yes, there is, but we will not.
like them from internal resistances.
Yeah, it is provable, but we will not do it now because of time constraint. I guess this is there in the NPTEL handouts that we have uploaded. The proof is there, and anyway, we will learn this proof in a second year subject. Okay, so for now, the proof is skipped.
Can you show the last slide?
So what did you told about the NPTEL handouts?
In the in this in under the file section of this team, there are some books, upload books, notes, etc. Shared that you may use. So one among them is these NPTEL notes. Okay, you can find
Okay,
it.
sir.
Okay, so now maybe we solve a few questions. Okay, so suppose we have a circuit, a circuit consisting resistance, resistors and DC sources, I mean DC voltage and current sources. It has two terminals, call it A and B. Okay, now if let this current be I, okay, if we sort A and B, then I becomes 4 ampere. If we connect a 3 ohm resistance between A and B, then I becomes 2 ampere. How much will be I? If we connect a 9 ohm resistance between A and B. Okay, so this is the question. Do you have any suggestion how you would like to solve this?
Sir, here IN would be 4 ampere.
I1. Sir, I equal to 1.
I equal to 1, you are saying. Let us see. Okay, so let us use Thevenin's theorem. Okay, so this circuit inside the box is, according to Thevenin's theorem,
Yes, sir, I is 1.
equivalent to one source in series with one resistance. Now, how much is this resistance? How much is this voltage? That we have to find out. Okay, now when this A and B are sorted, then how much is the current? That current will be VTH by RTH. Okay, that is given as 4 ampere short circuit current. This is also the Norton current. Okay, and then if you connect here a how much 3 ohm resistance, then we can write that VT, how much will be this current I? Then I should be
2
it is
2
given
ampere.
2 ohm, but how do you express it? It is RTH plus 3 ohm. This is equal to 2. Okay, so we have 2 equations and 2 unknowns, VTH and RTH. So you can solve VTH and RTH from here. So how do I do that? Maybe I can write VTH is equal to, from the second equation, 2 RTH plus 6, this is ampere, so this becomes volt. But from the first equation, so this implies RTH equal to VTH by 4 ampere. Okay, so this will be, therefore RTH is VTH by 4 ampere. I have a mistake somewhere. Oh, I missed 2 ampere here. Okay, so this ampere goes away. Okay, then plus 6 volt. So from this, how much is VTH? It will come out to be 12 volt.
12.
And once we know VTH, then RTH is VTH by 4, 3 ohm.
3.
Okay, and if so, now if I connect here 9 ohm resistance, okay, when 9 ohm is connected, then I will be 12 volt by 3 ohm plus 9 ohm, that is 1 ampere. answer. Okay, next let me take another example. I have two voltage sources connected parallelly. Plus minus, and anyway this is not given. Let this be 4 ohm and this is 6 ohm, and here we connect we have a 3.6 ohm resistance. This is A, this is B. Okay, and what else is given? This current is given to be 2 ampere, I equal to 2 ampere. Now the question is, if we replace this 3.6 ohm resistance with a 1.6 ohm resistor, how much will be I? Do you want to try it first yourselves?
Sir, 3 ampere.
Okay, let me see. So this
Yes, sir, 3 ampere.
Sir, are those two batteries or what of the same value or what? Like
that
4
is not
ohm,
given.
6 ohm?
That is not given, so I can't guarantee that. Okay, so consider the circuit inside the box. Okay, so this will be equivalent to a voltage source in series with a resistance, this is A, this is B. How much is RTH?
2.4.
RTH
2.4
is basically 4 ohm in parallel with 6 ohm, that is 2.4 ohm, right? Okay, then how much is VTH?
12 volts.
So
12
what we can write that VTH divided by RTH plus 3.6 ohm, this resistance is equal to how much? 2 ampere. So from here, now RTH is 2.4, so therefore VTH will be 2 ampere into 2.4 plus 3.6 ohm, that is 612 volt. So VTH is 12 volt. Okay, now if so, when we connect here this 1.6 ohm resistance in place of 3.6 ohm resistance, then how much will be this current? I will be VTH by RTH plus 1.6 ohm, that is 12 volt by 2.4 plus 1.6, that is 3 ampere. Absolutely right. Yeah, great. Okay. Okay, fine. So any questions so far?
Sir, once can you show the solution once again? Like
Anything else?
No,
Sir,
sir.
we can do these both the questions with Norton's theorem also, like I am doing that.
Yes. You can do using Norton's theorem as well.
And for that, the I is only in the outer circuit, means the resistance in which we are entering, that I we are considering, not that parallel RTH, the current in that.
No. I mean, we are not considering if this is I1 or if this is I2. We are not considering I1 and I2 at.
Yes,
Yeah.
we are
Okay. So
considering.
we are only
Okay, sir.
talking about this outside current. This is same as this current I. Okay, fine.
Okay, sir.
So next we will study about another theorem, maximum power transfer theorem. Okay, so suppose we have a voltage source together with some resistance. It may be the internal resistance, call it R, call this E plus minus, and here are the two terminals between which I can connect another resistance, call this capital R, and this capital R is variable. Okay, and then this current I, how much will be I? It will be
E by R plus small r. E by R plus R, capital R plus.
Yeah. Okay, now the power consumed by capital R is how much? That is I square R.
Yes, sir.
Which is E square by little r plus capital R square into R. Now observe that if I increase capital R, then you may say, okay, I square R may increase because R is increasing, but at the same time current is decreasing. So will the power consumed in R increase? Doubtful. At the same time, if you decrease R, current will increase, but since R is decreased, I square R will decrease. So now one thing you can observe that for a very large value of capital R, the current will be almost zero. Therefore, power consumed will be zero. And for very small value of capital R tending to zero, again the power consumed will be zero. So power, if I call this P, then P is a function of the capital R, outside resistance. Now we can ask for which value of R, for R
Smaller.
equal to how much the power consumed by the capital R will be maximum.
Smaller.
Yes, you are right. Absolutely right. Okay, so how do we determine this? So we can just differentiate this quantity with respect to capital R, dP dr, and yes.
Instead of that, can we write the denominator as R minus small r whole square plus 4 small r capital R? So for the power to be maximum, denominator should be minimum. So R minus R whole square should be 0.
No,
Therefore,
no. Just so you are saying that you want to write it like this: E square R by R minus R whole square plus 4RR
plus 4.
Okay.
So
now
for
you are
the
saying that this should be minimum, right? But see, the numerator is also variable. So numerator is not constant. So making the denominator minimum does not guarantee.
Then divide by R, sir.
You want to? Oh, you want to divide this by R, like this.
Yes, sir.
So this becomes, yes, you can also do that. like this, right? Now the numerator is constant. In the denominator,
by root r, sir.
yeah, so this denominator should be minimum.
Sir, it should be root r.
R by root r minus root r.
Yes.
Yes, sir.
Okay. Now, yeah. So now this quantity inside the bracket should be
Zero.
That's the minimum possible value. So that implies little r is equal to capital R. Yes, that is one way of proving it. Excellent for this new suggestion. Another way of doing it is you just differentiate this quantity and equate it to 0. Let me do it very quickly. So what do we get? E square is just constant, and then if you differentiate, you will get r plus r whole square minus 2r plus r into r divided by r plus r whole square whole to the power 4. This should be equal to 0. This will also give you that r should be equal to r for this derivative to be equal to 0. But you also have to verify, so this is your homework, verify that the second derivative is negative at r equal to r. I should rather write capital R equal to little r, because capital R is the variable. Okay. So this is the condition for maximum power being consumed by the external resistance. When this theorem may be useful, so one example is as follows. So at present during this class, I am using a headphone to communicate with you. Possibly many of you are also using headphone or some other speakers which is connected to your computer. Okay, so now you think the audio port of your computer is basically some voltage source. It has also some resistance. This is a source. This need not be a constant value source. Of course, it's not a constant value source, otherwise we will not get any sound. But it's a time varying source. You call it E as a function of time. And outside we have our microphones or headphones or speakers which has some resistance. So this is the speaker, and this is inside our computers. Okay, now how loud will be the sound that we hear? That depends on the power consumed in this resistance at any moment. Okay, so we may decide what should be the value of the resistance of the speaker so that we get maximum sound. So it should be equal to the internal resistance of the audio port. So that's an application. Okay. Now let me ask you one question. So we have already solved this circuit. Okay. Now let me ask, if I connect a resistance capital R between P and Q, which is variable, then for R equal to how much the power consumed in R will be maximum?
2.1 ohms.
2.1 RTH.
And how much will be the maximum power? is the, how much is the maximum power? Okay. So the first answer is very simple because this circuit is equivalent to a voltage source according to Thevenin's theorem in series with resistance RTH, and RTH we have already calculated 2.1 ohm. Okay, and how much was VTH? Do you remember?
5.
VTH was 5 volt. Okay, so R should be equal to RTH, that is 2.1 ohm for maximum power being consumed by R. And how much will be that power?
2.97.
2.97 watt.
0.97, approximately 3 watt.
That is given. Yeah, that is given by. So here we have. So here we are connecting a 2.1 ohm R equal to 2.1 ohm. So then this current I, if this current is I, then maximum power is R square 2.1. Sorry, I square into 2.1 ohm. Now I is how much? I is
5 divided by 4.2.
Divided by 4.2 whole squared into 2.1. So this is in watt. That will be the answer. And how much is this? So this is equal to 25 divided by 2.1. Am I correct? And watt, how much will be this? Little less than 12. About
25 divided by 8.4, sir.
Sir, there is a 4 missing in
Oh,
2.1.
yes, into 4.
It's a 4 times 2.1.
4 times that. So
2.97.
3 around
2.97.
2.9.
Around 3.
Yeah, I guess around 3.
3
Yeah, approximately. So you can check it. Okay, fine. I guess this is already 3, so we will take a short break, and meanwhile I just give you one question so that if you have time you can solve it. Okay, the question is, suppose this is connected here, and suppose this is connected here. Okay, and then the question is same. Okay, R is connected outside. So I have changed the position of these two external terminals. Okay, so it is connected to B and D respectively. So what will be the answer? Okay, so let's take a few minutes break and we will be back in 3-4 minutes. Meanwhile, we will solve it. Okay, welcome back. So what's the answer here?
0, sir, because VB and VD are both at 0 potential.
Yes. So the power consumed will be 0 definitely, and 0 watt, and for what value of R this will be maximum, it doesn't matter because it's always constant. Why is that so? Because the VB and VD, they are both at 0 volt, so the Thevenin voltage is 0 between VB and VD, between B and D, so no current will flow through the capital R. Okay, so with this we will start a new chapter in our course, which is on.
Then,
Yes, please.
sir, ET tutorials will be held from next week.
No, no.
What's the word?
Our first tutorial class is on 26th April. However, I will suggest that you try to finish the first tutorial much before that, because the gap gap between first and second and third and so on, those tutorials is not very much. So if you do not start earlier, you may be in a difficult position towards the end. So I request you start earlier. Yes.
So, sir, will we be added to tutorial means channel in MS Team, or will we be emailed about it?
I will give you all the details through email, etc.
Okay.
Okay, so consider we have a capacitor, parallel plate capacitor. Suppose the capacitance is C. The two plates are charged at plus Q and minus Q. Okay, and therefore the let me write it here, plus Q minus Q. Then the voltage between the two ends is how much? That is V will be equal to Q by C. Which side positive, which side negative? Left side positive, right side negative. Okay, and suppose here some current is flowing, which is I, and the same amount of current is going out from the other side, I. Okay, now if this current is flowing, then the charge Q will also change with time. So this will be a function of time. So the voltage will also be a function of time, and the current can also vary with time. Now we can write that I is equal to dq by dt. That's the current. Okay, and Q is nothing but C into V. C is a constant, so ddt of C into Vt, which is same as C dV dt. This is the current I. Okay, so this is the relationship between the voltage and current across or through a capacitor. Okay, now please note the directions of the voltage and currents carefully. We cannot we cannot draw something like this. If we denote the current and voltage in this way, okay, then I cannot write I T is equal to C dV dt. This is not correct. What will be the correct equation in this case? It will be minus I equal to C dV dt. Okay. So be careful about the directions of voltages and currents. Now consider that we have a battery plus minus a resistance. This is E, this is R, and let also have a capacitor. Let me also put a switch, and let me keep this switch open so the circuit is not closed, but the capacitor can hold some charge between the two plates. Okay, so and therefore there may be some voltage across these two plates. Let me call that voltage as V0, okay, plus minus. This is from here to here. Now the switch is open, so no current is flowing through the to the capacitor. So the charge of the capacitor will remain the same, should remain the same forever, and the voltage across it should also remain the same. Now, if I close this switch, the moment I close this switch, now current can flow to the capacitor, and therefore the capacitor charge can change, and also the voltage across the capacitor can change. Okay, so now let us ask how will the voltage across the capacitor change with time. Okay, suppose I denote the moment when the switch is closed as time t equal to 0, okay, and then let me call this voltage as Vc, which will be a function of time. Okay, so the capacitor voltage is Vct, and at t equal to 0, Vc0 is V0. That is dependent on the initial amount of charge that the capacitor had. Now, how will the charge change with time? Any question?
Sir, is the capacitor initially charged?
The capacitor may have some initial charge. Okay. Now,
okay.
Let me call this current as IT. Okay, so I is definitely 0 before t equal to 0. Now, after for t greater than equal to 0, that means after the switch is closed, okay, we can write a Kvl equation, KVL, say starting, if I call it A, B, C, D, okay, then the KVL says that the starting from A to B, we have a voltage E, then B to C, there is a voltage drop of R into I, and then C to D, there is another voltage drop of Vc. Okay, this is function of time, this is also function of time. This all together should be equal to 0. From this, we can write that R into IT plus Vct is equal to E. Now, how much is I? This I is same as the current that flows to this capacitor. So therefore, I is given by C into dVc dt. Okay, plus Vc, these are all functions of time, equal to E. We can rewrite this as right. Now we have a differential equation. So if we solve this differential equation, we will get Vc, capacitor voltage, as a function of time. Okay, so how to solve this type of equation? So we will come across similar equations again and again. So let me give you a common trick of solving this type of equations. So let me denote this as
it is a linear differential equation.
This is a linear differential equation, first order, and let me just call this 1 by RC equal to a constant, and the right side E by RC is equal to B, another constant. Now whenever you see such a differential equation where you have first derivative plus some constant times the function equal to some constant, whenever you have any differential equation of this form, to solve this you can use this trick. Multiply this equation with e to the power at, both sides. Okay, so let me write this way. Okay, so we have multiplied this equation by e to the power at. Why e to the power at? Because this coefficient in this term is a, therefore we are multiplying this with e to the power at.
It has become exact differential.
Yeah. Okay, then the left side of this equation can be written as d dt of e to the power at v c. This is a function of time, of course. Okay, and the right side I keep as it is. Please check, am I correct? If you differentiate this term, you will get this using the product rule. Okay, please check. Next what? Let me multiply by dt and integrate. And let me do this integration from some time t equal to 0 to t equal to say some other, in general t. Okay, so time 0 to any other time t. Okay, so if I do this integration, what do I get? The left side will become e to the power at vct from 0 to t. The right side is e to the power, b is constant, integration of e to the power at is e to the power at by a, let me put the a here, and this is from 0 to t. Okay, so then we can write e to the power, left side e to the power at vct minus e to the power 0 is 1 vc0, right side is b by a e to the power at minus 1. So finally we have, let me write it as v, so vc0 is v0, bring it to the right side, plus b by a e to the power at minus 1, and then divide by it, e to the power at, so you get vct equal to v0 e to the power minus at plus this will become b by a 1 minus e to the power minus 8. Is it correct? Please check. Okay, now if I put the value of b and a, what do I get? B was where is that? This B was E by RC and A is 1 by RC. Okay, so here we have E by RC divided by 1 by RC which is equal to plus E 1 minus e to the power minus 80. You may also write this in this way, E plus V0 minus E to the power minus 80. This is the equation of the capacitor voltage as a function of time. Okay, now let us see at t equal to 0 initial capacitor voltage will be how much? If you put t equal to 0, you will get E plus V naught minus E, that is V naught. Okay, and at t tending to infinity, how much will be the final voltage?
E.
Yeah, you will get E. Okay, so that means in this circuit, as you can expect, the capacitor starts from the voltage V naught, that is it depending on its initial charge, and finally it will get voltage equal to the voltage source, so that at that point current will become 0. Okay, so at final steady state, capacitor voltage will become equal to the battery voltage. Now you can also write this Vc t equal to, okay, by reorganizing these terms, you can write this as final voltage, which is E, plus initial voltage minus final voltage whole multiplied by e to the power minus 80. Okay, please check. Final voltage is same as E, initial voltage is V0. So this is also a equation which may be sometimes easier to remember. Okay. Fine. Any questions so far? Next, let us then plot how does the graph of this voltage looks like as a function of time versus VCT. Okay, so it starts from V0 and it reaches E. Okay, if V0 is lower than E, suppose this is V0, suppose this is E, okay, so we are drawing this graph okay, so it will start from here and then gradually, very slowly, finally asymptotically will reach E0. Finally E. Okay. Any questions so far here? Now, this is also equal to e plus v0 minus e to the power minus t by rc, because a is equal to rc. Okay, so we also sometimes write it as e plus v0 minus e multiplied by e to the power minus t by tau, okay, where tau is rc. Now what should be the unit of tau? And what should be the unit of
Second.
yes, because it is we have time divided by tau. Overall it should be unitless, so tau is has the unit of time. Okay, tau is called time constant. And what is the meaning of this tau, time constant? So tau decides how fast the voltage changes. Okay, so if I have a very large value of tau, how will be the graph? It will be very slowly increasing. So this is for larger tau, and if we have a very small value of tau, the graph will be like this. So this is for smaller tau. Now one more thing, you notice that the capacitor voltage changes by an amount of E minus V0 volt. This is in volt. Okay, because initial voltage is V0, final voltage is E, so this is the amount of change. Okay, so this is the total change the capacitor voltage will undergo. Now, in time tau, okay, in tau amount of time, okay, that means from t equal to 0 to t equal to tau, what happens to this voltage? So at t equal to 0, this voltage is E plus Vc is equal to E plus V0 minus E to the power 0. Okay, so that and at t equal to tau, Vc will be E plus V0 minus E to the power minus E to the power t by tau will be 1. Okay?
Minus
minus
1.
Yes, minus 1. Okay, yeah. So here the change in voltage is V0 minus E into E to the power minus 1. Sorry, 1 minus E to the power minus 1. And how much is this quantity, 1 minus E to the power minus 1? Can you check using your calculator?
0.63.
Yeah, so it is 0.63 times this. Okay, and this is the total change that we will have after a long time. Okay, so we see that in time in tau amount of time, the voltage changes by 63% approximately, 63% of the total change. So tau is the time required to accomplish approximately 63% of the total change.
Sir, for the change, we have to do final minus initial, no sir. You have did initial minus final. V at t equal to tau minus V at t equal to 0, no sir.
So is there should be a yeah, right. E to the power minus 1 minus 1. Now is it correct?
Yes sir, now it will become E minus V naught.
Yeah. Any more mistake there?
Under
yeah,
it
here
will
also it should be opposite.
E minus V naught.
Yes, yes. Thank you. Okay. Yeah. I hope now it's fine. Okay, please check. And if you have any other question, please ask, no problem. Any question, any doubt? Okay, then, so we saw how VC changes. So VC is, as you have seen, E plus V0 minus E to the power minus T by RC. And then how will be the current I? Which current I'm talking about? I'm talking about the current here. Okay. So how much will be that? So for that, let us do the derivative. So I is equal to C dV dt, C dV C dt. So that becomes C. And if you do the differentiation, you will get V0 minus E to the power minus T by RC, then minus 1 by RC. Okay, and then this is equal to E minus V0 by R to the power minus T by RC. And how will the graph of this current look like as a function of time? Yes. So in how much
decaying.
is the
Decreasing exponential.
Yeah. So this will be decaying exponential. How much is the initial current? Initial
E
current
minus V
is
naught by
E
R.
minus V naught by R, and finally it is 0. At t tending to infinity, it is 0. Okay. Achha. Now one thing we observe that at t tending to infinity, I t becomes 0. Okay, so let us go back to the circuit. So in this circuit, after a long enough time, this current becomes 0, so no more current can flow, and at that point, actually this capacitor acts like infinite resistance or open circuit. Okay, so t tending to infinity, the capacitor behaves like open circuit, infinite resistance, and this is called the steady state. What do we mean by steady state? Steady state in this case in DC circuits means when all voltages and currents are not changing with time anymore. Okay, when voltages and currents have settled down. Okay, so they are not changing anymore. So anyway, I mean, if we look at this equation here, or maybe here, if we look at this equation, when we reach steady state, that means derivative of voltage should be 0, because steady state means voltages and currents are not changing anymore in DC circuits. So this term, the first term will become 0. So then Vc will become E. So at steady state, Vc will become E. This comes from the definition of steady state. And if Vc and E are equal, so then the voltage across this resistance R is same. There is no voltage gradient across this resistance, so current will become 0. Okay, so steady state implies current to be equal to 0. Also, we can also say that I is C dV dt, and this should be equal to 0 because the derivative should be equal to 0 at steady state. Otherwise, we cannot call it steady. Steady means, in DC circuit, steady means voltage and currents, they are all settled down to some fixed value. Okay. Fine. Any questions so far? So I shall take one example next. Okay, so the question is, if this voltage is Vc across the capacitor, and if this current is I, find Vc as a function of time and I as a function of time after the switch is closed at t equal to 0. So initially the switch was open, and then at time t equal to 0, the switch is closed. Okay, after that, how this voltage and current will change as a function of time. And assume that the circuit was in a steady state before the switch was closed. Okay, so can you suggest how to solve this question?
So Vc is 10 volt at time equal to 0.
Yeah, so yeah, observe that before the switch is closed, okay, so before the switch is closed, that means this resistance is not there, I mean, it's not effective before that. Then we have this 10 volt source directly connected to the capacitor. Okay, so the capacitor charge at that time will be equal to the battery voltage, which is 10 volt. So VC is equal to 10 volt before, on or before, at the moment before the switch is closed. That means t equal to 0, before t equal to 0. That is one observation. Now, what happens after t equal to 0? So, after t equal to 0, we consider this part of the circuit to have its Thevenin equivalent. What will be the Thevenin equivalent of this circuit inside the box? Definitely it's a source with
10 volt and 2.4 ohms.
Okay, and we have the capacitor connected here. This is 1 millifarad, and
Sir, if in the Thevenin circuits, if there are any capacitors, then what should we do?
if there is another capacitor inside
In
the
the Thevenin
box,
circuit.
inside the box, if there, then we cannot do it in this way. Okay, so we will learn only the simpler cases in this course and how to solve more general cases, more difficult cases that you may learn second year onwards. Okay, so for t greater than equal to 0, okay, we and at that moment the switch is closed. Okay, switch closed. How much will be the Thevenin equivalent voltage? VTH. That will be the voltage between terminal A and terminal B. No, that is not 10 volt. Is that 10 volt?
4 volts. Yes.
That is, so when this is closed, we have, let me draw here, then we have 1 ampere current flowing here, okay? Because 10 divided by 6 plus 4, 1 ampere, and then across the 4 ohm resistance, the voltage will be 4 volt. Okay, is it okay? Otherwise you may ask, no problem. Okay, and how much?
Sir?
Yes.
Sir, can you repeat how you got the voltage?
Okay, so let me okay, so we are considering for t greater than equal to 0. That means this is closed. Okay, so for t greater than equal to 0, and we are considering the circuit inside the box. So here are the 2 terminals. Okay, now what is the Thevenin voltage between these 2 nodes? That is the voltage across 4 ohm resistance. Okay, now how much is the voltage across 4 ohm resistance? Apply potential divider rule. Okay, so you get 10 volt divided by 4 plus 6 into 4. That is 4 volt. Correct? Is it okay, or I can repeat again? I can elaborate more.
It's okay.
Okay. Yeah. So that is the situation for t greater than equal to 0 after the switch is closed. So VTH is 4 volt. And so this is the Thevenin circuit. Thevenin's equivalent. And now how much is the resistance between A and B?
2.4.
So
2.4
RTH is basically 6 in parallel with 4. 4 ohm parallel 6 ohm, that is 2.4 ohm. Okay, so this is 2.4 ohm. Now this circuit, okay, this circuit is same as this circuit here, right? We have battery, voltage source, resistance, capacitor in series. Here also we have voltage source, resistance and capacitor in series. So if this is VC, okay, plus minus, this is the direction, current I is in this direction. So from the knowledge of the solution of the previous circuit, what can we write? VC will be of the form its final value plus initial minus final value whole multiplied by e to the power minus t by RC. Okay, so we are using this formula which we have derived. Okay, so now in this circuit, how much will be the final value? Final voltage?
4 volt.
It should be 4 volt equal to the source voltage, so it is 4 volt. How much is the initial voltage? It was initially it was 10 volt.
10 minus 4, 6.
Okay, so
10 volt.
10
Initially it was 10
minus 4 volt e to the power minus t by RC, and R is 2.4, C so is 1, so this becomes 2.4 millisecond. Okay, so that's the expression of the voltage. Okay, 4 plus 6 e to the power minus t by 2.4 millisecond.
Sir.
Yes.
So, so what happens is here the capacitor will charge the battery, right?
Capacitor will get discharged. Whether the battery will get charged or not, that depends on whether the battery is rechargeable. That may be, but capacitor will get discharged.
Sir,
Then
how
where
is
will
initial 10?
One at a time. Nalini?
Then where will be the discharged current go, sir, from the capacitor?
Discharge current?
So like, will it go in the form of heat?
Yeah, it will. If it is not chargeable, if the battery is not chargeable, by default it will go as heat dissipation. Yes.
Okay, sir.
Okay. And
Sir,
then,
how is initial 10? Can you please?
yeah, initially, where is the question? Yeah. So initially, this is the circuit, right? And the switch was open. When the switch is open, then what do we have? We have only this 10 volt, 6 ohm, and 1 millifarad in series. Nothing else. Okay. So this voltage source is connected to this capacitor, and then at steady state, the capacitor will become equal to the voltage source voltage, 10 volt, right?
So initially 0, no?
No. Why it should be? See, initially this is open.
Yes,
so
sir,
it's
it
like
will be
this.
0 because delta V is 0 only, right? Q is also 0.
Initially
So,
it acts like a wire, no?
See.
Short circuit.
Initially, this is how the circuit is. Okay, this is how the circuit is. Now,
Yes,
now if this circuit is kept in this way for a long enough time, then what will happen? This capacitor will get charged to this 10 volt, right?
Okay, I got it. Sir.
Now, the question says that
So it is kept open for a long time.
it is kept in that way for a long time because the question says that the circuit was in a steady state before this switch was closed. That means it was kept for a long time in that way. Okay, fine. So yeah, finally, how will be this current? So that will be just C dV dt. C is 1 millifarad, farad C into dv dt, that will be 6 e to the power minus t by 2.4 millisecond, and am I doing any mistake? And then divided by multiplied by minus 1 by 2.4 milli is the so milli goes away, this will become ampere. So initial, so that means this is 6 by 2.4 e to the power minus t by 2.4 millisecond. So how much is the initial current? Initial current is 6 by 2.4 is how much?
2.5.
2.5 ampere. And if we look at this circuit, so initially yeah, I guess that's fine. Yeah. No, I have a mistake somewhere. Minus.
I is negative.
Hello?
Sir, will I be negative here? 2 point. Sir.
Yes. Yeah, yeah, this is minus, this is also minus, this is also minus. Yes, right, you are right. So this should be negative. Because why negative? Because the capacitor was initially at 10 volt, and then it is finally going to finally 4 volt. That means it is getting discharge. Getting discharge means current is actually flowing in the opposite direction. So therefore current is negative initially. Yes, I was missing this minus sign. Thank you. Thanks for pointing out. Okay.
Sir, like just in case such a same question comes in the paper and the question says that write the value of the current flowing, then there is no need to write the sign, right?
It depends on the question. If the questions asks you for the magnitude of the current, no need to write the sign. If it is given like this, the arrow is given, and if I ask how much is the value of I at t equal to 0, since the arrow is given, then you have to definitely write it as a negative current. Yeah.
Okay. Okay, sir.
Okay. So I will stop here. It's already 4 o'clock. So if you have any question, you may ask. I shall try to answer. Otherwise, the class is over today.